Hello, my name is Zach Stone, and today I'll be talking about Lewis dot diagrams. Lewis dot diagram shows the bonding between atoms and lone pairs in a molecule. These diagrams can be used to predict the shape of the molecule, bond angles, bond energy, bond length, and polarity, but we will mainly be focusing on the shape of the molecule. Let's use methane as an example. So the first step is to find the total number of valence electrons in the structure. So carbon will have 4 because it is in group 4, hydrogen will have 1, but since there are 4 hydrogen atoms, there will be 4 electrons in total. To find the number needed, every element wants 8 electrons except for hydrogen that wants 2, beryllium that wants 4, and boron that wants 6. So carbon will have 8, and each of the hydrogen atoms will have 2, which comes to a total of 16 electrons needed. If you subtract the number of electrons methane has from the number of electrons methane needs, and divide that number by 2, you will find the total number of bonds in the structure. However, this method does not always work. Generally, when drawing the structure of the Lewis dot diagram, we make the least electronegative element the central atom. However, hydrogen is never the central atom, and therefore carbon is the central atom in this structure, even though it has a greater electronegativity. Now that we have the structure down, we're going to draw in our single bonds and then count the electrons, remembering that each single bond counts as 2 electrons. So there are 4 single bonds times 2 electrons per each single bond, and that is a total of 8 electrons, the same number of electrons methane has. And our dot diagram is finished. Let's use nitrate as another example. So we know that there are 5 electrons in the nitrogen and 6 electrons in each of the oxygen atoms, which comes to a total of 23 electrons. But since it has a -1 charge, we need to add 1 more electron to 23 to get the total number of electrons that nitrate has to be 24. And then there is 8, and then nitrate needs 8 electrons for each nitrogen and 8 electrons for each oxygen, which comes together to a total of 32. And 32 minus 24 is 8. Divided by 2 equals 4, so there will be 4 bonds in the structure. And on the right, I have started organizing the structure of the Lewis dot diagram, and nitrogen will be in the middle because it is the least electronegative. Now in blue, we draw in the single bonds, and we fill in the remaining electrons. And as we can see, there are 24 electrons, so many people would think that we're done. But if you haven't noticed, nitrogen only has 6 electrons and is not following the octet rule. So if we look in red, here we can rearrange the electrons and add a double bond so that nitrogen now follows the octet rule, and there is still a total of 24 electrons. The octet rule states that the valence shell of an atom is completely filled, and it gives the atom the same electron configuration as a noble gas. In some cases, atoms will have more than 8 electrons in their shell, and they are considered to be expanded octets. We also need to take resonance into consideration when drawing the nitrate ion. This means that we need to show that not any oxygen atom is favored over any other oxygen atom because it is receiving the double bond. So you can see in each of these pictures, the double bond is at 3 different atoms, oxygen atoms, and you also need to draw the structure in brackets with the minus sign in the top right corner and little arrows in between each of the possible structures. This is the final answer for the Lewis dot diagram of the nitrate ion. Xenon tetrafluoride is an example of a molecule with an expanded octet. So let's calculate the number of electrons this molecule has. So there is 8 valence electrons in xenon and 7 in each of the fluorine atoms, which comes together to a total of 36. And there's 8 for the xenon because it's already full, and there are 8, and it needs 8 for each of the fluorines, which comes together to 40. So if we subtract 36 from 40, we get 4, and divide that by 2 to find the number of bonds, which is 2 bonds. And we can see that this is clearly not possible, so we can ignore this rule at the moment. So next we want to put xenon in as the central atom because it is the least electronegative, and add on the surrounding fluorines. So we want to fill all the fluorines with the remaining electrons, and we realize that we are 4 electrons short of our goal of 36. So what we need to do is throw these extra electrons onto the xenon atom as we did, and this would be the final electron dot diagram for the xenon tetrafluoride molecule. Another example of a molecule with an expanded octet is phosphorus pentachloride. And on the left, I simplified the has-need table because that's always necessary once you get a lot of practice. And we calculated that it has 4 bonds, it needs 48 bonds. So 48 minus 40 is equal to 8. And that divided by 2 is 4 bonds, which we know cannot be possible because 5 chlorine atoms cannot bond with 1 phosphorus atom using only 4 bonds. So on the right, we made phosphorus the central atom because it is the least electronegative, and we attached the remaining chlorine atoms with single bonds, and we added the remaining electrons to the chlorines. And we checked our work by making sure that the total number of electrons in the structure was 40, and it was. So this is the final electron dot diagram for the phosphorus pentachloride molecule. Each one of the molecules we worked with today has their own molecular shapes. CH4 has 4 bonds in 0 lone pairs, and therefore is a tetrahedral. NO3- has 3 bonds in 0 lone pairs, and therefore is trigonal planar. The xenon tetrafluoride has 4 bonds in 2 lone pairs, therefore giving it a shape called square planar. And the phosphorus pentachloride is trigonal bipyramidal because of its 5 bonds in 0 lone pairs. I hope the electron dot diagrams and the molecular shapes are helping you visualize the molecules that you are working with. Thank you.